Hi everyone, looks like it's time. Looks like I have till 5 o'clock, so I'll try and stay within that time limit. Hi everybody, well, nice to see you. My name is Laura Flores. I'm a Rados engineer at IBM, and today I'll be talking to you about the new rebalancer that was added for Reef in Ceph. So first, why is rebalancing important for Ceph? In distributed storage systems like Ceph, it's important to balance both write and read requests for optimal performance. To balance writes in a cluster means to ensure fast storage and replication of data in that cluster. And reads on the opposite end is to ensure quick access and retrieval of data in a cluster. And both are equally important. You might be thinking we already have a balancer in Ceph, but this existing capacity balancer, also known as the FMAP balancer, works well to balance write requests, but it does not handle read requests, which is why we wanted to focus on this for Reef and Ceph. So first I'll talk about some differences between capacity balancing and read balancing. They're not direct opposites by any means, but they both have different things going on. So capacity balancing, which is balancing writes in a cluster, we consider that a functional requirement. This is because it's a strict requirement for Ceph to function properly. If a device fills up, we lose capacity of the entire cluster, so this is important. As opposed, read balancing is a performance requirement. This is not a strict requirement for Ceph's functionality. However, it helps the overall system work better and perform better. What this means is that unbalanced reads leads to a reduced overall cluster bandwidth. Now, let's look at the operations of balancing. Capacity balancing is actually very expensive. It requires data movement by definition, and this means that it takes time, during which the performance of the system is greatly reduced every time we balance. Read balancing, on the other hand, is actually a very cheap operation, which is promising for future improvements. The reason it's cheap is that it's just a metadata operation. It's very fast and it involves no data movement. There's no impact on the cluster performance except when we see ideally improved performance when the operation completes almost immediately. And what I mean by metadata operation is that we're looking at the PGs that are already involved on that, or the OSDs that are already involved on a PG, and simply changing the primary of the PGs that are already, or of the OSDs that are already involved there. The last difference, capacity balancing, we assume, we know that it balances the write performance if all devices are homogeneous, meaning that they're the same size and performance. Read balancing, this first version of the read balancer also assumes that all devices are homogeneous, same size and performance. However, in future versions, we can use this same mechanism to improve the overall cluster performance in heterogeneous systems, which is important since depending on whether you have a small ODF cluster of all the same size or a larger cluster that's heterogeneous. I'll go into this more later, but the read balancer will be great for balancing small ODF clusters, but it has great promise as we increase the complexity of the algorithm to accommodate heterogeneous systems. So I always like to come up with a real-life example to explain balancing, and I like to know the difference. So first I'll use this example of a library to explain how capacity balancing works in a cluster. So up there we have three to the left. Kind of hard to point and keep my mic on, but we have 3 bookcases. And on the first bookcase, we have 6 book groups. And as some of you might have already connected, this is similar to a 3 OSD cluster with 16 PGs, where the book groups are PGs. In the top left bookcase, we have 6 PGs. In the one next to it, the second bookcase, we have 4 PGs or book sets. And on the bottom, we have 2 book sets. This is an unbalanced capacity situation since the first bookcase is a lot more full with PGs than the other 2. And in a Ceph cluster and in a library, we want this balanced equally. So after using the upmap balancer, which is either enabled automatically through the manager module in the Ceph cluster, or you can use the OSD map tool to create upmaps, or you can run the commands by hand. Either way, you can balance the cluster or balance this capacity in a library by moving 2 books from the first bookcase down to the bottom bookcase. And this leaves us with 4 book groups or PGs on the first bookcase and all the rest. And this gives us a balanced capacity. Now let's balance primaries in a library. For this, I had to kind of think about how we could talk about it in a library, but let's just say that all of the books on the left hand of the bookcase are the most important books, or the primaries. On the first bookcase, we have 4 books to the left. So there are essentially 4 primaries on this bookcase. On the second one to the right, on the top, there's one primary book to the left and 3 to the right. And on the bottom, there's the same configuration, 1 book set to the left and then 3 to the right. Although this is a balanced capacity situation, we want an equal number of important books on each bookcase, or an equal number of primaries on each OSD. And this is where the rebalancer comes into play. And this is actually what you'd see more in an ODF cluster, where all of the bookcases or all of the devices are the same size. So it's easy to see what needs to be done. And what we do is we moved two book groups over to the right on the first bookcase, since that one had too many. And then we moved 1 over to the left on the second bookcase to give that one another important book or another primary. And we did the same for the bottom one. So now all of the bookcases have 2 important books on the left. And in a cluster, this would mean that each OSD has 2 primaries. And now we're balanced capacity-wise and primary-wise. So what did primary balancing look like before Reef? Because there was something there, we just don't have a dedicated mechanism until Reef. So to emphasize, there was no active balancing code or dedicated primary balancing mechanism before Reef. However, on homogeneous systems, like in a small ODF cluster of devices of the same size, the crush random distribution would improve the number of PGs. Or so actually on smaller clusters, the crush statistics don't always work out in the favor, but the more PGs you add, the crush statistics work to balance the primaries, and it's a bit more balanced that way. And that's my second bullet point. In general, larger systems are quite balanced, but smaller systems like small ODF clusters may not be balanced. And we sometimes see extreme unbalanced situations occur on small homogeneous clusters, like in the bookcase example. If we look at what happens with heterogeneous systems, not all large systems have the same OSD sizes and the same performance. So you might increase your system over time and add devices of different sizes. And ultimately, it's really hard to keep everything of the same performance and of the same size. So it does become heterogeneous and with unbalanced primaries. So in conclusion, the rebalancer, which is the first phase of the workload balancer offered in Reef, will be mostly useful for ODF clusters or small clusters of the same size devices, because we operate on this assumption. However, the workload balancer, which is people have asked, is this merged yet or not. This is more of all ideas at the moment, but the workload balancer will be based on the rebalancer infrastructure and will be used to improve this algorithm to accommodate large heterogeneous clusters. So I'll talk about some work that has been merged to Reef. And this is specific things that you'll see when you upgrade to Reef, and you'll see all these new things. So in the Ceph command, Ceph OSD pool ls detail, we've added for replicated pools. This is, by the way, read balancing is only applicable to replicated pools. We've added a new metric called the read balance score. And I've highlighted this in green for pool number 6. It's a replicated pool. And the red box at the bottom says the rebalance score is 1.50. And I'll explain exactly what this means as we go on. But if you look at the bottom, there's an erasure-coded pool, and this does not have a rebalance score since primary balancing is only applicable to replicated pools. Now I'll explain the meaning of the read balance score. So in most cases, and I say in most cases, assuming that primary affinity is the same for all OSDs, in most cases, an optimal score is 1. And in a lot of cases, we can't achieve this perfect score, but the closer we get to 1, the more balanced the reads will become. The score is built to be in the range of 1 to replica count. So if the replica count is 3, the score can be anywhere from 1, which is perfect balance, to 3, which is the worst balance. A score of 1 plus x shows approximately x times 100 of degradation in the pool read performance under load. So the previous example was a score of 1.5. That would be roughly 50% degradation. And in this case, I wrote a 1.2 would be roughly 20% degradation. So that was the output of Ceph OSD pool LS detail without adding a formatter. But if you add the JSON or the XML formatter, you'll see even more details added to the rebalance score. We have the acting score and the stable score, which are based on the acting set and the upset, respectively. We have raw scores, which I'll explain more how that goes in the second slide or in the next slide. And we also have some metrics about what the average primary affinity is and primary affinity accommodated with weights, different weights. So the score that you see and the output of the main score you see when you would run OSD pool LS detail is the raw score divided by the optimal score. And again, the weighted info we added takes into account OSDs that are of different sizes. And in this screen grab, all of the OSDs are the same size, which is why average primary affinity and average primary affinity weighted are the same. But if the OSDs were different sizes, they would be different numbers. And this is all in anticipation of future improvements that we'll add to the workload balancer to accommodate devices of different sizes. The next stepping stone we added was new commands that can be used to reassign a primary to a PG. So some of you may be familiar with the Ceph OSD primary temp command. However, this command isn't as maintained. It's very old. And from our testing, we saw that it only updates the acting set in a PG. But this new command makes sure that when we're assigning a new primary to a PG, we check that the OSD is already part of that PG, and we make sure that it's a valid mapping. And it changes both the upset and the acting set. So in this example, I've run the Ceph command pg dump pg's brief, and we're looking at pg 6.1. And we see that the PG has an acting and an upset of 1, 3, 2. And these are the OSDs that are involved in that PG. And OSD number 1 is the primary. But say we want to change the primary from 1 to 3. We would run the command ceph osd pg upmap primary 6.1 3, and this means that we are changing the primary of PG 6.1 to OSD 3. And if we check the output of PG dump, we can see that change has occurred where the primary has been assigned. And if, say, you try to map it to OSD 0, that OSD is not participating in this PG, so it would give some kind of error message. It would say this is not a valid primary mapping. So the high-level design of the current rebalancer code in Reef looks a bit like this. We handle one pool at a time. This is important since we're only looking at a particular workload one at a time. We calculate the desired number of primaries that should be on each OSD. And to do that, we take into account the number of PGs divided by the replica count, and we multiply that by primary affinity. So if you ever end up setting an OSD to primary affinity equals 0, this would mean that it would get 0 primaries. And no primaries would be assigned to it, even if that would be more optimal. Next, we take that desired distribution, and we swap which OSD is the primary on select PGs to achieve this desired distribution. And again, no data movement is involved. Swapping only occurs with the OSDs that are already involved in a particular PG. And this means the operation is very cheap. Now, I'll run through some slides of a demo I did on a vStart cluster. And at the end of the slides, I've included all of the scripts I used in a GitHub repository if anybody's interested in trying it out. So first, this isn't a necessary step, but I've run the Ceph status command to show you that this vStart cluster has 4 OSDs, 2 RGW daemons, 7 pools, and 184 PGs. Now we'll check the pool details for the current rebalancer scores. So I run the command ceph osd pool ls detail, and I believe this would be available in OSD dump 2, anywhere in the OSD map. So I've highlighted pool 6 in particular because we can see it's an RGW pool, and we can see that the read balance score is 1.63, which is roughly a 63% read performance degradation. And I think we can improve this. Next, we'll use this command to get the latest copy of the OSD map. So something important is that the rebalancer is an offline tool at the moment. So if you're familiar with the OSD map tool, I'll show you how, but this is how we're going to do first a dry run and then apply it to a live system. But currently this is more of an offline option. So we'll get the latest copy of the OSD map. And it's important, as we did with the bookcase demonstration, we need to make sure the capacity is balanced first, because the first phase of the read balancer assumes that capacity is balanced. So what I've done there is I've taken the OSD map tool, I fed it the OSD map, which I've named OM, and I've specified that we're running this in upmap mode, and I've given it an out file. And the out file, if there were any changes made, would contain Ceph commands that we can apply to a live cluster. However, on this particular vStart cluster, there were no further optimizations to be made. The distribution was already perfect, so that's great. Now we'll run the read balancer, focusing on the earlier pool we talked about, default RGW control. So I taken the OSD map tool, given it the OSD map we pulled from earlier as a parameter. This parameter, next parameter, isn't necessary, but I specified --vstart because all of the commands then are prefixed with /bin. It's annoying to have to add that in. So if you're working from a vStart cluster, you can add this in, but it's not necessary if you're on a regular cluster. Then instead of upmap, you'll pass in the --read flag to say that we're balancing in read mode. And then we specify the out.txt file, and I'll show you what this file contains, but if there are any optimizations, this is where we'll see all of the optimizations with the new commands we added. And then lastly, we feed in a read pool, and you can only do one at a time, and we've given the default RGW control pool. So running this without any debug involved, we see that there's been an improvement. If there's no improvement, it will say as such, but we see the before distribution, OSD 0, 1, 2, and 3 had a different number of primaries on them. OSD 0 had 10, OSD 3 had 13, while OSD 2 had only 3, and OSD 1 had only 6. So, and that resulted in a score of 1.63. And after we've found that the primaries have been distributed perfectly, which doesn't always happen, but in this case it did. And the score has been moved down to 1, and now each OSD has 8 PGs. And this is considered a dry run because we haven't applied any of the changes yet. We've taken our OSD map and essentially done a dry run so we can check the results and see if we even want to apply them to our cluster. And there were 9 changes calculated, which we'll see in the next slide. So I've put the output of what was in the out.txt file, and as you can see, it contains a series of commands that we added for Reef, the PG upmap primary command. And these commands can either be run by hand, or this is my next slide. They can either be run by hand, or you can apply them directly by using the source command. So I've run it source out.txt. And this is working from my live system, my vStar cluster. And this is applying all of the 9 changes to that cluster directly. Now I'll output the Ceph OSD pool LS detail. And we remember we improved pool 6 default RGW control. And now the read balance score has gone down from 1.63 to 1. And that means that ideally we'd be at 0% degradation. Future plans and improvements involve documentation. So all of what I've put in the slides, this will be put into the documentation so that it's very clear on what you need to do to use the OSD map tool and how the dry run works, etc. And also explaining the new metadata that's been added to the OSD pool details. We are also, this was a question in the town hall discussion earlier, whether performance tests have been, or results have been achieved. This is a work in progress right now. I'm actually working with Mark Nelson to conduct some tests so we can see how the read balance score correlates with the actual performance improvements in the cluster. And when these results are concluded, I will have them up either in a Ceph blog post or somehow publicized, but either way, I have my GitHub repository linked at the bottom where all of this information will be held. So if you're curious for further updates, you can always check there. Next improvement, we plan to add the read balancer to integration tests in Toothology so that this can be regularly tested on the Rados suite. We also would like to, after we've had more early adopters, which if this looks interesting to you, please try it out and let me know how it goes. We would like to turn this on by default as part of the Balancer Manager module, as the upmap balancer currently is. And lastly, and almost most importantly, we would like to, in future iterations of the read balancer, we would like to account for devices of different sizes so we can handle heterogeneous systems. And that's it for the read balancer. Thank you very much. Does anyone have any questions?
What about user building?
One second.
I know why there's no easy support for now, but can you comment on it?
Read balancing is only applicable to replicated pools. I can't really go into more detail, but it's the fact that we're dealing with replicas here, and that's not a concept in Razor-coded pools. So everything that's calculated depends on the number of replicas involved, and that's simply not a thing in erasure-coded pools.
But you could move the primaries only, even if it costs data movement.
On erasure-coded pools?
Yeah, I think so. I mean, it's an idea.
Certainly, yeah. I think that would just be a different concept for what we're going for. But I would be. I also wanted to mention my colleague Josh Solomon was a huge helper in all of this. So I would certainly bring that idea to him, as he would have likely more things to say. But he and I have worked together on this, so I can absolutely bring that idea to him and see what he thinks.
Fantastic, Laura. Very, very good work.
Thank you.
So my question is, would there be any advantage in applying all of these primary changes in a single Ceph command versus having it done incrementally over possibly dozens of commands?
That's a good question. So the current algorithm is written so it's a greedy algorithm. So we go through and iterate through the PGs and choose an optimal solution, but it's not necessarily the optimal solution. So a single command would likely be the optimal solution. Or we could also make it into one, but for now we've made it, this really connects with the new commands that were added, the new PG upmap primary command. And if we had a command that allowed you to make multiple changes at once versus one, we wanted an option if somebody wanted to simply play around with their cluster and change the primary on one of their OSDs, and they would just run the single command. And we were also going off of what currently exists with the upmap balancer with the primary upmap command. But that's not to say that we could do that. So I think that's a really good question and something I would like to look into further.
Hi, I don't have any homogeneous clusters, so would you say definitely don't run this for quite a while?
You can try. It may not. It's not like something will break. First of all, this is a very safe option as it's an offline tool. So if you want to just play around with your OSD map on a replicated pool, please by all means do so. The only issue is that it may not be the optimal solution for your cluster. So I would recommend on a non-homogeneous system, run it on your replicated pool, see if the score improves. And if so, you can check the results and see if you would like to apply it to your system. And you can always try it out. And if you don't like it, there's the complementary command that removes those primary up maps. So you can always play around with it and see how it improves your cluster. And that would actually be really good feedback for us to hear, since we would like to handle heterogeneous systems. Obviously, there will need to be more work put into what's currently there, but it would be nice to see early results.
Thanks.
I got another one for you, Laura. Would you, if we're using this tool, would you also turn off the autoscaler? Because I could see it constantly messing up the work that this is doing.
Good question. That's interesting, because if the autoscaler is constantly moving things around, you might want to try disabling it. I guess I don't have a hard and fast recommendation for that, since this is a new feature. But if you're finding that you're running these upmap balancer commands, it's making the changes, but then you check your score and it's decreased again, then I would maybe try disabling the autoscaler. But the metric you can check to make sure is to see if it's being affected or not is that metric we added in the new the OSD pool details.
It might be a little bit evil, this question, but if I apply your read balancer to multiple pools except one, is the score of every pool evaluated for a run or just the single pool? Because the evil part is I can make this last pool, which I did not apply the read balancer to, well, being pretty much placed on one OSD with all its primaries.
So you're saying if you ran the read balancer on all of your pools except for one,
Yeah.
the read balancer is so. Say you have
Does it take the other scores into its calculations at all, or only for this pool you're applying it to?
only for that pool, I believe. Yeah, I think it's only for that pool. So if you ran each score takes into account the number of PGs divided by the replica for that pool, if that answers your question.
So can I'll get back to that later.
Sure. Yeah, it's a tough question. This is great because in all of my experiments, I went through specific iterations, but always looking for new corner cases.
How unique the tool is comparing to OMAPs? Because you were saying that it's offline tool, so I could take Quincy OpMap and play with that.
Yes, so that was another question asked in the town hall, whether this could be used potentially in Luminous. I would say possibly no, because the new commands that were added are there's for Reef, so you actually have to enable that your client is compatible with Reef before running the commands. That's not to say that it couldn't be backported. As far as Luminous, no. But to Quincy, I'm not saying it's impossible. So if there's enough interest in Reef, there's enough similarities that I would consider doing that. But at the moment, the commands are for Reef specifically. So if you tried to run them on Quincy,
but if I don't want to run, if it's an offline tool and I'm extracting the OMAP and playing around with that, in theory, I just get the results if my cluster is bad shape or not.
Yeah, so my thought is perhaps the OSD map tool would output these new commands in the out file, but if you're in Quincy, those commands wouldn't exist. However, you might try and replace primary PG upmap primary with primary temp, because that does exist in Quincy. But that command isn't as maintained, and it only changes the acting set of a PG. But that's not to say you couldn't edit the out file or run the commands by hand and replace it with primary temp and see how that goes. Because again, my only hesitation with Quincy is that we introduce these new commands which are only available in Reef. I hope that answers.
At least for me.
Have you guys considered a network between the clients and the OSD primary? Because even if you rebalance it, it may make it worse because the clients may be far away from primary OSDs now.
Perhaps that has to do with data movement, but this doesn't involve data movement. Is that something?
No, if you consider a 3-node cluster, a client may have been with the same OSD, which was primary before on the same node, but after this kind of movement, the primary may be in another node. So the network latency may increase, and this may lower performance. Have you guys taken into consider?
Yeah, nothing originally guaranteed that they were local like that in the first place. The feature you're actually looking for is local reads, and that's independent of this. The primary moving is, local reads allows you to read from not the primary, so changing the primary doesn't matter.
Okay. Yeah. So
Again,
this is
nothing in the original distribution would have guaranteed the primaries were in the right place.
okay.
So you couldn't have been relying on that.
Yeah, so this is basically in regards to OSD's own performance of serving reads.
It's more about aggregate read throughput when all of the OSDs are addressable by all of the clients. If the
Okay,
client has a
okay.
significant network division to a portion of the OSDs, then you would be using a different feature set.
Okay, yeah. Next.
Thanks, Sam.
So is the goal here to add this to the balancer? So it kind of happens transparently in Manager?
Yes, that is a goal, to add it as we get more adopters and are more confident with the results. We would like to add this to the manager module, as is the up app balancer, so that users wouldn't have to run it, make those decisions on their own, and that it would happen automatically. That's certainly what we plan.
Very cool.
Any more questions? I have a question for you guys. Who is willing to try the read balancer in Reef? That's great to hear. And I realize I don't have my email, but it's I can, if anybody wants it, it's Flores, Flores @ibm.com. And if you have any questions at all, please email me. And I'm really open to questions, and I'd also love to just hear how the read balancer is working on your Reef clusters, or not Reef. Thanks, everyone.